Hey everybody, welcome to the Unknown Ketone Lab. Here's the outline for this video. I'll be going over the experiment in general and talking about how this lab will work. I'll show how to characterize the unknown ketone, the different techniques involved, and then I'll show the experiment in the lab. So in this lab, you'll actually be given two unknown ketones to identify. One will be given to you as a liquid, and you'll identify it based off of its boiling point, a derivative melting point, which I'll go over later, and then using TLC. And here's the list of the 10 ketones, one of which will be given to you, and your job is to figure out which one you were given. So here are all the boiling points for each of the ketones, the melting points for the derivatives, and the retention factors for those derivatives on a TLC plate. And then you'll identify the second ketone using a proton NMR. So you'll be given an NMR for one of these 10 ketones. You have to figure out which one it goes to and then label the peaks. Now let's talk about how we'll characterize the actual ketone given to us in the lab. We'll start off by measuring its boiling point, which will happen here when the vapor pressure is equal to the atmospheric pressure. At that point, the liquid will readily turn into a gas, and the temperature should remain the same, and we'll measure that as our boiling point. That boiling point can be a little inaccurate for a variety of reasons. One, the atmospheric pressure is going to be slightly lower at a higher elevation, so we can already expect the boiling point to be a few degrees lower than the literature value. And two, that boiling point can be off depending on how close the thermometer is to the boiling liquid. We want it just a few millimeters above so that it measures the temperature of the vapors before they have too much time to cool off. Another problem that some students have is that they don't end up seeing a lag in the thermometer, and that's usually because they are boiling their ketone too quickly and it boils off into a gas too fast for a lag to really show on the thermometer. So we'll want to progressively heat up the ketone until we reach that nice reflux where we should see a steady temperature on the thermometer. Now, even if we did get a really accurate boiling point, it would be difficult to characterize the ketone just based off of that because some of the boiling points can be really close. So we'll want some additional tools to help us characterize it, and in this lab we'll be doing a derivative reaction. And this is how that will work. We'll react the ketone with 2,4-dinitrophenylhydrazine, which will form a hydrazone derivative where the ketone has now been added to the hydrazine portion of that molecule. This hydrazone derivative will end up being a solid, and each derivative will actually end up being a different color, either reddish, orange, or yellow, depending on the R groups attached to each ketone. And since this new compound is a solid, we can take its melting point and compare that to the boiling point of the original ketone. This kind of chemistry was a lot more common before NMR spectroscopy made it obsolete. For example, here's a page from an old chemistry book with a table of organic derivatives of ketones. So we have a list of ketones, and we can see the melting points of the hydrazone derivatives of each of those ketones if that reaction works for the specific ketone. And there are other derivative tests that could be done as well, but these tables were compiled so that when analyzing some compound like cyclobutanone, you could take its boiling point and then take the melting point range of its hydrazone derivative as a second way to characterize and confirm that you did actually have that ketone. To do this reaction, we'll dissolve the 2,4-dinitrophenylhydrazine in 4 milliliters of methanol and add 6 to 8 drops of hydrochloric acid. If it doesn't dissolve, then we can gently heat it up and add some more HCl. Once it's completely dissolved, we'll split the solution in half into a separate conical vial and save half of it for later. We'll come back to that. But we can add 50 microliters of our unknown ketone and let it react at room temperature for a few minutes. Once that's done, we can separate the derivative formed using vacuum filtration and acquire the melting point range. Each of those melting points is given to us in the table, and once we have the melting point range for the derivative, we can then compare it to the boiling point that we took for the original unknown ketone. So let's just say that we take the boiling point of our ketone and we measure it to be around 161 degrees Celsius, which could easily be for either of these two ketones, but that's too close to be confident in guessing which one we actually had. But luckily, the melting points for the derivatives are very different from each other, and we should be able to distinguish which one we actually had based off of that information. If the derivative melted within this range, then we could pretty confidently say that we have this compound. But if the derivative melted within this range, then we would say that we actually had this compound. Obviously, there is still room for error, so there is a third tool that we'll be using to confirm everything, and that will be thin layer chromatography. If we look back at the table, all of the retention factors for each of the derivatives is given to us using 9:1 methylene chloride hexane solution as the mobile phase. So what we'll do is react the other half of the hydrazine solution with 50 microliters of a standard ketone, and that standard will be of the ketone that we think we have. For example, let's say that we measure the boiling point of our ketone to be around 145 degrees Celsius. So we might assume that we have 2-heptanone, and we'd also assume that the derivative would melt around 89 degrees Celsius. But when the melting point range was acquired, it actually ended up being between 145.2 and 146.3 degrees Celsius, which now means that we most likely have either cyclopentanone or a slightly impure cycloheptanone. And it also means that we probably didn't take a very accurate boiling point. The melting point range that we got seems to be right on the literature value for cyclopentanone, so we're going to assume that that is the ketone that we have, and we'll take the remaining hydrazine solution and react it with 50 microliters of a cyclopentanone standard. Once that's reacted and we've separated the standard derivative using vacuum filtration, we'll take some of the unknown derivative and dissolve it in methylene chloride in a test tube. Then we'll dissolve some of the standard derivative in methylene chloride in a second test tube, and finally dissolve a mixture of both derivatives in methylene chloride in a third test tube. So we'll have 3 separate test tubes, one with the unknown derivative dissolved in methylene chloride, one with the standard derivative, and one with a mixture of both derivatives. Then we'll take a TLC plate and spot it with the 3 solutions, making sure to use a clean pipette each time, and develop it using 9:1 methylene chloride hexane solution as the mobile phase. Once the TLC plate is developed, we'll hopefully be able to see whether or not we were correct, and in this case, the standard derivative does not match up with the unknown derivative, and the middle spot for the mixture shows 2 different spots, meaning that they are 2 different compounds. So our initial guess of cyclopentanone was not correct. If we calculate the retention factor, it looks to be around 0.65 to 0.7 maybe, which seems to be more on point for cycloheptanone. If we were to do this again using cycloheptanone as the standard rather than cyclopentanone, then the TLC plate would end up looking like this, where all of the 3 spots match up, confirming that we actually had cycloheptanone rather than cyclopentanone. So once all of the data has been gathered, it is up to us to make our best educated guess on which ketone we actually had based off of that data. And then for the second unknown ketone, you will be randomly given one of these 10 NMRs, and your job will be to figure out which ketone it goes to, draw the molecule, label all the hydrogens, and then label all of the peaks like we've done in all of the other labs. Okay, so here we have the unknown ketone. I'm going to get a milliliter and add it to a conical vial so I can measure the boiling point. I'll attach an air condenser and insert the thermometer, placing it just a few milliliters above the liquid. And I'm also going to insulate the conical vial using some glass wool and aluminum foil so that the boiling point can be measured as accurately as possible. And when I place that on, I want to leave a little V-neck or a little opening so that I can see the liquid inside and know when it's boiling. So now I'm going to start heating things up, and we can see the temperature rising slowly as the conical vial begins to heat up. And we can actually start to see some condensation on the side of the glass, and eventually the ketone will start to bubble. But the temperature is still rising, so we're not going to measure the boiling point quite yet. until a good reflux is observed with condensation a few centimeters up the glassware. And now if we take a look at the thermometer, it's holding pretty steady around 122 degrees Celsius, so we'll measure that as our boiling point. Once that's done, I'll move on to the derivative reaction now. So I'll weigh out 100 milligrams of the dinitrophenylhydrazine and add that to a 5 milliliter conical vial with a large spin vane. Then I can add 4 milliliters of methanol and 6 to 8 drops of the 12 normal hydrochloric acid. I'll start to stir that to get the dinitrophenylhydrazine to dissolve in that solution. And after a couple minutes, I could tell that it wasn't dissolving super well, so I started to heat it up slightly and added a few more drops of the acid. After a few minutes, everything seemed to be dissolved a lot better, so now I can take half of the solution and transfer it over to a separate conical vial. Then, using an automated pipette, I'll transfer 50 microliters of the unknown ketone to that solution so it can begin reacting. And you can see the yellow color of the new derivative solid forming as it spins. I'll let that react for a few minutes at room temperature, and once it's done, I can transfer the solution over to the Hirsch funnel to separate the derivative solid. I'll rinse the conical vial with some sodium bicarbonate, as well as the solid on the Hirsch funnel to help remove any acid that would be left over, and I'll also rinse it with some cold distilled water after that. The solid can be stirred on the Hirsch funnel until it's nice and dry. Then I'll remove it from the funnel so that I can measure the melting point range. I initially put it in around 170 degrees Celsius, and it melted pretty instantly, meaning that it's not one of the derivatives with a really high melting point. So I put it in after that around 135 degrees Celsius, and nothing happened, so it's going to be one of the intermediate melting points. I started to raise the temperature slowly, and the solid looked like it was shrinking slightly, but I didn't see any liquid forming until about 142.8 degrees Celsius, and it looks like it finished completely melting around 144.6 degrees Celsius. So that'll be the melting point range. Now, both the boiling point and the derivative melting point seem to be pointing to cyclopentanone as the ketone, so I'm going to make another derivative using cyclopentanone as the standard and see if that matches up on the TLC plate with my unknown derivative. I'll stir the remaining half of that solution just in case any of the dinitrophenylhydrazine came out of solution. Then over in the hood, the standards for the 10 different ketones will be provided. So I'll find the one labeled as cyclopentanone and transfer 50 microliters over to the hydrazine solution. I'll let that react for a few minutes at room temperature again, and then remove the derivative from the solution following the same exact technique as before, rinsing it with some sodium bicarb and some distilled water. Once it's been left in there for a few minutes to dry, I'll remove the standard derivative from the Hirsch funnel, and before even developing the TLC plate, we can see that the standard derivative is the same color as the unknown derivative, so that's a good sign that we picked the right one. On the left, I have the unknown derivative, and on the right, I have the standard, so I'll add the unknown to the left test tube, the standard to the right test tube, and then I'll mix both of them in the middle test tube. Then I'll add enough methylene chloride to each test tube to fully dissolve the solid. And spot the TLC plate with each solution, making sure to use a clean pipette each time so that they don't contaminate each other. I'll use the 9:1 methylene chloride hexane solution as the mobile phase, and as the TLC plate develops, we can see that the spots are moving pretty closely together, so that's a good sign, but we'll wait till it's fully developed to decide whether or not we guessed right. Once it's done, it does look like there was only one compound per each spot, and they seem to have the same RF value, so it looks like cyclopentanone was a pretty good guess.